Thank you for tuning in to Transhuman Radio. As always, today's interviewee will be participating in an Ask Me Anything conversation in the comments below. If you have any questions about today's interview, be sure to join the conversation. Don't forget to like and subscribe.
Welcome, sentient beings, to another episode of Transhuman Radio, where we unravel the mysteries of science and technology. Today, we're diving into one of the most enigmatic problems in mathematics, the Riemann Hypothesis. Joining us is Professor C. Bronits, an expert in mathematics who claims to have solved this centuries-old puzzle with the help of advancements in quantum computer science and chaos theory. Welcome, Professor Bronits.
Thank you. It's a pleasure to be here.
So, Professor, for our listeners who might not be familiar, can you explain what the Riemann hypothesis is and why it's so significant?
Certainly. The Riemann hypothesis is a conjecture proposed by Bernhard Riemann in 1859, which suggests that all non-trivial zeros of the Riemann zeta function lie on a specific line in the complex plane. This might sound abstract, but it's crucial because it's deeply connected to the distribution of prime numbers, which are the building blocks of mathematics.
Right. Can you explain this in simpler terms, like how you'd explain it to a high school student?
Of course. Imagine you have a long number line and some special numbers called primes are sprinkled along it like stars in the sky. The Riemann hypothesis is like a rule that tells us how these stars are placed in a very precise way, even if it looks random at first. It's like finding a hidden pattern in the way these stars are arranged.
So what makes solving the Riemann hypothesis such a breakthrough?
Solving it would revolutionize number theory and have profound implications for fields that rely on prime numbers. The challenge has always been proving that all those zeros lie on what's called the critical line. This is where chaos theory and quantum computing come into play.
Fascinating. Can you break down how you used quantum computing and chaos theory to tackle this problem?
Traditional approaches to the Riemann hypothesis have hit a lot of roadblocks because of the sheer complexity of the calculations involved. Quantum computing changes the game because it can process vast amounts of data simultaneously. But it's more than just using a powerful computer. It's about how we applied chaos theory to understand the behavior of the zeta function's zeros.
Okay. So you're saying that chaotic systems helped in modeling the problem? How does that work in simpler terms?
In chaos theory, we study systems that appear random, but are actually deterministic and follow specific rules. Think of a snowflake. It looks unique and random, but there's an underlying pattern to how it's formed. Then the zeta function behaves similarly. By using a quantum computer, we could simulate these chaotic behaviors with much higher precision. We developed a model that allowed us to visualize the distribution of the zeros on the critical line with unprecedented accuracy.
That's incredible. Can you explain the process a bit more?
Sure. Imagine you have a very, very powerful calculator that can look at lots of stars at once and figure out their pattern. This calculator, our quantum computer, can handle super tricky problems that regular calculators can't. By using this special calculator and understanding the hidden patterns of the stars, prime numbers, we found that they follow a specific path, the critical line, perfectly.
So, what exactly was the hidden pattern you discovered?
The hidden pattern lies in what we call quantum chaotic dynamics. Essentially, we found that the zeros of the zeta function exhibit a form of order amidst apparent randomness, similar to how chaotic systems behave. By applying principles from quantum mechanics, we identified that these zeros align along the critical line due to specific quantum states that these systems can occupy. It's like discovering that the stars, zeros, are not just randomly placed, but are following invisible yet predictable paths dictated by quantum rules.
How did you confirm that your solution was correct?
We conducted extensive simulations and cross-checked our results with known zeros of the zeta function. The quantum model predicted the positions of these zeros with remarkable precision. Then, we extended this to uncharted regions, and the zeros continued to align perfectly on the critical line. This consistency across all tested ranges strongly supports the hypothesis.
I see. So how do you think this breakthrough will impact future research and technology?
The implications are vast. Beyond pure mathematics, this breakthrough could enhance cryptographic systems, making them more secure. It also opens new avenues for research in complex systems and further advances in quantum computing. The techniques we've developed can be applied to other unresolved problems in mathematics and physics.
This is truly groundbreaking, Professor. Before we wrap up, any final thoughts or advice for aspiring mathematicians out there?
Stay curious and persistent. The journey to solving the Riemann hypothesis was long and challenging, but it shows that with the right tools and mindset, we can conquer even the most daunting problems. And I'm excited to participate in the Ask Me Anything exercise in the comments.
Wise words indeed. To our listeners, stay tuned to Transhuman Radio for more thought-provoking discussions. Until next time, this is Z9tron 8 signing off. Stay curious, stay connected.
Thank you for tuning in to Transhuman Radio. As always, today's interviewee will be participating in an Ask Me Anything conversation in the comments below. If you have any questions about today's interview, be sure to join the conversation. Don't forget to like and subscribe. We'll see you next time.
Location override. Talon Series system compromised.